I
Well,
said
hello,
1, 2, 3,
everyone.
go.
You have been listening to me try and sort myself out. Hi, I'm Dr. Victoria Lemieux, and I am co-lead of blockchain at UBC. And I'd like to welcome you to this month's monthly research talk. So we're really delighted here to have with us today Joseph Bonneau, who's an assistant professor of computer science at New York University. If you've done any reading in blockchain literature at all, you'll be familiar with Joseph's name. His research focuses on computer security, including the economics and usability of security and novel applications of cryptography. He received his PhD from the University of Cambridge and completed postdoctoral fellowships at Princeton, Stanford, and Stanford University and the Electronic Frontier Foundation. And he's worked in industry at Google, Yahoo, Microsoft, and Cryptography Research, Inc. And in his spare time, which I don't know how he manages to find, he enjoys traveling, climbing, and kayaking. So welcome, Joseph. I won't reiterate what you're going to speak about today. I'll let you jump right into your talk, and thanks again for joining us.
Sure, thanks for having me. And yeah, sorry, I guess everybody can't see me. There's some sort of snag with the setup, so I'm not able to turn my video on. Yeah, I was going to say, speaking of travel and kayak and climbing, those were all things I was hoping to do when I made it out to UBC in person to give this talk. I think we originally were targeting spring 2020,
right?
So over a year ago. So, you know, sad that the pandemic is delayed till now, but and sad that I'm not out there in Vancouver in person to see everybody, but such is the world.
Yeah, we look forward to an opportunity to have you actually come and visit us soon, though.
As soon as I can, yeah, I would love to. Just yeah, as soon as the border opens up. Let me share my slides.
Yeah,
okay, so
my video off now.
Okay, so hopefully everybody can see my slides. Feel free to just stop and ask a question, or you know, type a question in the chat. I'm happy to answer questions as I go. But I wanted to talk about about lotteries in general, and the connection to blockchains, and the connection to verifiable delay functions, which has been exciting, quickly growing sub area of crypto the last couple years that I've been, you know, excited to be a small part of. So I guess more abstractly than a lottery, cryptographers think of this object called a randomness beacon. So this was initially thought up in the 80s as an ideal service that would just spit out randomness continuously. So at regular intervals, it would output new, fresh randomness. And this randomness would have a couple of nice properties. It would be unpredictable. Everybody would see the same results, and this service would sort of always run and output lots and lots of randomness. So if you had a service like this, you know, you could replace most lotteries that you think of today. You could determine the results of the lottery using this randomness beacon. Hopefully with another property, which I won't talk too much about, but is kind of overshadowing everything people want to do in this space. If you really want to start talking about replacing big high stakes lotteries, hopefully this randomness beacon is something that people believe in, that they actually believe all these properties hold, especially unpredictability, and there's some convincing explanation. So like I said, the killer application of randomness beacons is lotteries. There's a couple of reasons why lotteries are important. The thing that people think of first when they think about lotteries are games and gambling, things that are kind of fun. People think it's fun when unpredictable things happen. Pretty integral to lots and lots of games people play online and offline. So we sort of inherently need lotteries for lots of these applications. But the more important applications that people don't think of right away are where we have some sort of indivisible resource that, you know, somebody has to be given to somebody or some set of people. And for one reason or another, it's not the most fair way to determine who gets that resource is by a random lottery. So there's lots of applications of this. The United States and other countries run lotteries for immigration permits, for visas. So there's a large one that's run in the US every year. International sports lotteries are run for seeding. In lots and lots of places, lotteries are run for school assignment for places in schools, and also within schools for things like housing assignments. So these are all lotteries under the hood, even though they're very important, and they have really high stakes in money or in people's lives. And I think it's important to think about these applications, to think it's it's not the applications aren't, it's easy to think that games and gambling are sort of frivolous, but just trying to make the point that there's really important consequences to some lotteries. And there are also a lot of things that are lotteries. We just don't think of them as lotteries because they're not lotteries that you want to win. You can think of them as negative lotteries. Maybe the most famous example in the US was the Conscription Lottery, the draft lottery that determined who was forced to serve in the military. But there are a lot of other things that still happen today, usually around the idea of randomly picking people for audit or for extra security screening. And it's kind of important security for various security protocols that you can audit randomly, because then an attacker doesn't if an attacker is trying to say cheat on taxes or rig an election by manipulating some number of polling places, if they don't know where the auditing is going to happen, then they can't avoid attacking in those places. Okay, so if you want to run a verifiable lottery, most of the steps should be pretty straightforward to computer scientists. I have this slide more when I talk about lotteries to policy crowds. But essentially you commit to some algorithm that represents the lottery, and this could sort of be anything. It could be as simple as picking one person out of n candidates. There could be a lot more complicated rules. For example, when they do a lottery for seeding in the FIFA World Cup, there's a lot of rules about how many teams from the same confederation can appear in the same group and so on. But the only thing that really matters is that you can write down all the rules of the lottery in code. In fact, you can really think of lottery as just a randomized algorithm. There should be some period once the algorithm is committed to that members of the public can audit it. They can see that it actually implements the lottery process that we want. In the blockchain context, you can think of the algorithm commitment period as sort of posting a smart contract to the chain, and then people can look at the source code for the smart contract before they decide whether they want to interact with it. Then the one really important step, which essentially the rest of this talk is going to be about, is choosing a random seed. And cryptographically, we know that you only need to choose a very small random seed, and then you can simulate as much randomness as you want with a pseudo-random number generator. So essentially, you can input a random seed of about 128 bits, and then you can run any randomized algorithm you want for as long as you want. So once you have the random seed, you just execute the algorithm. And then, there's various different models for this, but any observer, member of the public, can rerun the algorithm to verify that the published result is correct. Maybe you use succinct proofs, verifiable computation, so that people don't even have to do independent verification. They can just check a proof if that's more efficient. But either way, there's some process where people can check that the lottery result is correct. So like I said, steps 1, 2, 4, and 5, we know how to do with standard tools. The trick is really choosing that random seed in a way that everybody can get behind. A couple of other applications of randomness beacons that I'll just show because they're kind of neat. One is for zero knowledge proofs. So we've, if you've learned about zero knowledge proofs, if you've studied them, you know that the verifier usually has to behave randomly. for security. This is, by the way, very similar to the way that you want to randomly choose whose taxes to audit or who to select for additional security screening at the airport. You want the verifier to ask a random query so that the prover can't kind of cheat in advance and be ready for it. So, traditionally we think about interactive protocols. There's a standard way to produce non-interactive proofs, but there's also a different way to do it that maybe you haven't seen before that uses a randomness beacon, which is kind of neat. If you have an append-only log like a blockchain, a prover can sort of commit to their zero knowledge proof, or you could think of it as like the first step in an interactive protocol. They could then draw randomness from the randomness beacon. And later in the append-only log, they can sort of simulate queries from a random verifier using the randomness beacon, and then post the answers to the log. So you can sort of simulate interacting with a verifier that's making random queries just using a randomness beacon. Kind of a neat idea. The other application, which is quite relevant to blockchains, is consensus protocols. So there's sort of this, it's now a folk theorem. I think it's been argued more formally in a couple of different places. But this idea that if you want to have an efficient consensus protocol that scales to lots and lots of participants, you can't have everybody talk. You have to somehow randomly choose within each block or within each epoch of the protocol a random committee who act in that round. Okay, so we see versions of this in all sorts of different consensus protocols. And there's a cool historical example. In ancient Greece, they had the idea of randomly picking members of parliament who would deliberate and make discussions. And this idea is called sortition, that instead of having a vote by all voting members of the public on every matter of interest to the state, you randomly pick a parliament and then have them vote on everything. And of course, if you have a random sample of the population, you'll get pretty accurate results if you'd had everybody vote on it, but a lot more efficient. Again, not everybody has to communicate if you just randomly select a small committee and change it ever so often. So this device you're looking at, this big stone with all the slots, was called, I believe, a clariterion. I'm probably pronouncing the ancient Greek poorly, but it was a device where people would come and drop this stone disc into one of these slots, and then it would sort of randomly bounce around, and they had a small chance of being selected, basically as a member of parliament for the next term. So you can think of modern blockchain consensus protocols doing sort of a similar idea. Nakamoto consensus used in Bitcoin and many other places. It basically uses a random selection process to choose a miner to choose the next block. The problem, as we all know, is that this randomized process is who can solve the proof of work first, which is really, really expensive and has a lot of side effects. But it's one way of solving this problem of randomly picking who should act in the next round, or who has the authority to act in the next round. So there's this trilemma proposed, a situation where there's like three properties you want for your consensus protocol, and it's hard, possibly impossible, to achieve all at the same time. And those properties are determinism, not relying on randomness. Sublinear communication, that's just a fancy way of saying that not every participant has to speak in every round. You want only a small subset of people to have to speak so that it's efficient. And you want adaptive security. And adaptive security means the consensus protocol is secure even if the attacker can choose adaptively some group of participants to corrupt. So it helps to look at this, I guess, by example. So classic BFT protocols that have been around for a long time, they can run deterministically. And by deterministic, I just mean that the honest participants don't need to rely on randomness. Now, maybe they need randomness for the signature algorithm part of it, but putting that to the side, assume that they have secure signatures. And there are secure signature schemes that don't need randomness. But anyway, so those protocols are they're secure against adaptive corruption. They can run deterministically, but they have this downside that everybody has to talk. If you want to have a deterministic process that had sublinear communication, you could think of sort of doing Nakamoto consensus, but just round robining, just cycling through all of the different nodes in the system and giving them each a pre-assigned slot of when they're allowed to choose blocks. The problem with that protocol, which I'm not sure anyone's ever seriously tried to do in practice, but the problem with it is that it's not adaptively secure. Since there's a predictable order of which nodes create blocks at which slot in the chain, an attacker, if they want to, they can just corrupt a series of nodes in a row, and then they can sort of have a long run where they're able to corrupt all of the blocks. Okay, so that's efficient and deterministic, but it's not secure against adaptive corruption. Most of the blockchain space, instead, to get adaptive security, which we want, and also sublinear communication, are not deterministic, and that means that they need randomness, and essentially a randomness beacon would make them go. So not just Nakamoto consensus, like I argued, but proof of stake protocols. They all rely on sort of randomly, the efficient ones at least, all rely on randomly selecting a committee that can't be predicted in advance, so that an attacker can't just compromise the whole committee before it's their epoch to act. Okay, so that's how there's kind of this deep and interesting connection between your randomness beacons and consensus. Okay, so I'll talk about different ways we could try to build a randomness beacon. It's worth going through a couple of interesting, maybe intuitive ideas that don't quite work. So one that always comes up is we could try to base our randomness beacon off of what you could call a natural beacon, or some sort of phenomenon in nature that's too difficult for human beings to control. So solar flare activity on the surface of the sun, cosmic background radiation. The weather, people sometimes suggest. That example's kind of getting less good because there's places where they do control the weather to some extent by cloud seeding. But anyway, you can think of these things that happen in outer space and say we don't have the ability to control what's happening on the surface of the sun, and it is unpredictable. The problem is that it's not really unanimous. Observing what the beacon value is means we have to look at the sun. We have to somehow convert that to a digital signal, and different observers might get slightly different values when you discretize it. And once people don't agree on the beacon value, it's kind of useless. So I've given this challenge many times. If there's anything happening in space that can solve the unanimity process, somehow it produces a binary outcome that's very clear, that would be really great. I've talked to a couple of astronomers, and they've never had a good idea that would solve this problem. But maybe it's out there. It would be neat to find. There's always kind of the default solution to any problem in cryptography, which is just have some trusted third party do it. That does exist. There's a service called random.org, which is sort of the first thing you get when you Google this. And they'll give you a random number. The problem is that you're trusting this one organization to produce it. There was an attempt by the U.S. National Institute of Standards, NIST, to actually do this. They ran a beacon for a while. They actually stopped, but when they did run it, they output some randomness every 60 seconds and signed it. And they had a very nice story about how this was generated by some quantum mechanical device that was in a basement in Maryland somewhere. The problem again is that you had to completely trust NIST that they were actually putting the randomness generated from that device up on this web page, and not just sort of making it up to their own ends. So the solution that people mostly have used in practice, dating back, the idea is so old. This picture's a mosaic dating from the Roman Empire, is to just use devices that generate randomness physically. So Things like rolling dice, putting balls in a hopper and picking them out, drawing things out of a hat. Those are all still used. This is amazingly, this is sort of state-of-the-art technology that's used and filmed on TV all the time when you want to convince the public that a result is actually random. So, probably everybody has seen a version of this on TV at some point in their life. So, it can make for a really good show and be a lot of fun and be dramatic. The problem is that, if you've ever seen a magic show, you should intuitively realize that, people can make things look quite random that actually aren't, that are going to a specific value. And there's some pretty good examples of that from practice. So there have actually been lots and lots of cases of lottery draws that have been manipulated. There's one that they even made a movie out of. And the more recent one, which is pretty fun, the I guess disgraced ex-president of FIFA, Sepp Blatter, he claimed that UEFA, the European Football Association, was rigging draws for the European Championships for years. And his claim, if you look at the bottom of the screen here, is that they would put some of the balls representing certain teams in the refrigerator or the freezer so that the host on TV could reach in and feel the cold ball and know that that was the one to pull out first. So, is Sepp Blatter credible? I don't know, but this exact same idea has been alleged to have happened at NBA draft lotteries too. So a very simple example of how you could rig this sort of random looking draw and not leave any evidence of it on the TV broadcast. There's also one example, I think, which is pretty interesting, of physical randomness just failing, not because of any ill intention, as far as we know, but just producing bad randomness. So 1969 was the first year during the Vietnam War that a conscription lottery was held, and it was a big televised event. The men drawing these balls here were actually members of Congress. They chose one member of Congress from each party to try to convince the public that this was a fair draw. But they had a very interesting flaw. They put, it was actually 366 capsules, because it was one for each day of the year, and then you got a priority number based on your birthday. But they dumped them in this large drum in order. And then they turned the drum on its side to rotate it, which was designed to mix the capsules up. The problem is that, they were only rotating it on one axis. So, it mixed a lot up and down, but it didn't really produce very much motion to mix the capsules side to side. Then they turned the drum back on its side, and they just had, a member of Congress drawing them out. So naturally, you're more likely to grab something that's toward the top. And like I said, since the mixing was sort of side to side, the numbers that started on top were generally still on top at the end and were generally picked first. And it introduced a strong bias in, well, not a strong bias, but a statistically very strong, very significant bias in the order that was given, the priority order that was given. It's a little bit hard to see, but if you stare at this scatter plot, it should jump out at you that there's a lot more weight in this upper left and this lower right corner, and not very much in these corners. And again, that's the bias that actually these were later days of the year got lower. So essentially, people who had December birthdays were unfairly more likely to be targeted for the draft. So one other idea for how to build a lottery that's been around for a while, besides this physical generation, which has a long history, and I'll come back to it later in this talk, is to use data from the stock market. So this slip you're looking at here, this was basically handed out in New York City in the early 1900s by local organized crime. And the idea basically was that you could gamble on three digits that would be taken from, it was different in different cities, but I believe in New York, they would take the total amount of shares traded on the New York Stock Exchange the day before and take the three least significant digits from from that. So they would send a representative around to different neighborhoods, and if you wanted to bet for the day, this was before state lotteries were legalized. You would basically pick 3 numbers, and then this right column indicates how much you bet, how many dollars, and you would make 1,000x your money back if you happen to get it right. And the idea, basically is that stock market data, financial market data, is very hard to predict. If you could predict it, you'd make lots of money, obviously. So there's actually like deep economic theory that says you shouldn't be able to predict what tomorrow's stock prices are going to be, or how much volume is going to be, how much volume is going to be traded. And this actually has a big advantage over the natural phenomena like weather or sunspots, in that there is consensus. Everybody sees the same results. So it's actually like pretty promising as a way to create a randomness beacon, with one small problem, which is that there are some people in position, large players in the market or high frequency traders, to try to manipulate this data to rig the beacon. So just interesting historical idea. And like I said, I'll come back to it later in the talk. But I want to tell you about the cryptographic approaches to solving this problem. So the classic one that you may have seen at some point, there's a lot of different flavors of it, but commit reveal protocol. So this is like a simple example of a commit reveal protocol with 3 players. The goal at the end is that they're going to generate a random number that none of them individually can influence. So you can think that in the first phase of this protocol, everybody posts a commitment to a random number. And of course, the commitment, there's a lot of commitment schemes in crypto, but it can be as simple as just compute a hash of your random number along with a nonce. And then later, once everybody's committed, everybody reveals what their random number was. And you generate the beacon result by combining everybody's random number. So you could, say hash all the random numbers together, XOR them together, lots of different ways you could do this. Okay, and the idea is that since everybody has to commit to their number before they've seen anybody else's number, nobody can know at the time that they commit how the number they're picking is going to influence the final result. And in fact, it should have the property that as long as one of these parties chooses their number randomly, the total result should be random in the end. So it's a really strong model. Actually, you only need to trust that one party in this protocol acts honestly, and the final result should be random. So far so good, but there's a Achilles heel to this whole family of approaches, which is that the last person to reveal, if they want to, can shut the whole protocol down. So imagine that Alice and Bob both reveal the random number that they committed to. At this point, Carol knows what the final outcome is going to be, because she can see Alice and Bob's random numbers, and she knows her own random number that she committed to. But she's the only one who can see it at this point, because nobody else knows what random number she committed to. So she's kind of in this unique position where if she chooses not to reveal her random number, the other 2 are never going to know what the result would have been. And you basically would have to restart the protocol. So if Carol wants to, she can just sort of rage quit and refuse to finish the protocol here and force them to start over. And that might be a good strategy if she doesn't like the outcome. Say if they're playing a game or a lottery between them, and Carol's going to lose if she reveals. Right, and the insight is that the last person to reveal kind of learns the result before everybody else, and then has this opportunity to bias the result. So this approach is actually used in the blockchain in lots and lots of places. There's a couple of ways to try to save it, but the general approach that is used a lot in the context of blockchains is that you make everybody publish some sort of bond, and they or deposit, and they lose that money if they don't reveal. So that works pretty well. You give people a financial penalty if they don't reveal. The problem then is that like ties up a bunch of money and deposits, and introduces this financial cost to the protocol. Okay, so there's a whole other family that you'll see in a second when I try to list all the papers that have come out in the last year or two. There's a huge family of randomness protocols that build off of some ideas from threshold crypto or multi-party computation. I'll just show you kind of the simplest version of this that uses a cryptographic tool called publicly verifiable secret sharing. Okay, so you can see this protocol's a lot more complicated. It's philosophically pretty similar to the commit reveal idea in that everybody commits to a random number and the result is a combination of everybody's random number. But the idea here is that you publish enough additional information so that if one party or sometimes more than one party drop out, the other parties can get together and reconstruct what that party's random share was. Okay, so the way that this works, we'll just look at the values Alice publishes here. So she publishes a commitment to her random number, and then she publishes, she secret shares her random number. So she splits her random value into two shares, one for Bob and one for Carol. And then she publishes an encryption of both of those shares under those parties' public key. So that, if need be, Bob and Carol can get together, they can both decrypt their shares and they can reconstruct what RA, Alice's random number, was. And then at the end, she has to publish a proof that says that all of this was correctly constructed. Okay, so if all goes according to plan, like the simple case is that everybody just reveals what they committed to, and then you construct the final beacon output. But if somebody drops out, if Carol tries to do that attack where she forces a restart, Alice and Bob can basically, they can publish, the corresponding share they have of what Carol's randomness is. There's some way to reconstruct what Carol's random nonce was from, these two shares that she sent to Alice and Bob. And then, it's possible for Alice and Bob, even if Carol has completely gone offline, to reconstruct what the result would have been if Carol had just done, the normal thing and published, R sub C down here. Okay, so it's really the commit reveal protocol. You're just using a bunch of crypto so that if someone drops out, you can reconstruct what they would have done. Like I said, there's lots and lots of extensions to this idea. In particular, the version here is really simple. It's just a three-party protocol, and any two parties can recover if one of them drops out. You can extend this to have any threshold you want of participants is able to reconstruct what happened if somebody else drops out. So like I said, this is probably not even a complete list, but the past 3 to 4 years have seen like a huge explosion in papers about various ways to do this. There's lots and lots of ways to try and streamline this and pipeline things and get the efficiency up. So there's been a lot of great work on doing that. There's some similar protocols that build on threshold crypto instead of secret sharing. Similar idea though. And in fact, you can frame the entire problem of generating a randomness beacon with a group of people as just a multi-party computation problem. So, we know that we can do MPC for any, well, at least anything in NP, which is certainly true for this this randomness beacon problem of combining everybody's random nonces. So if you wanted to, you could use like generic MPC techniques to generate a random beacon. Those would probably be much slower. These highly streamlined protocols are going to be faster, but it does mean that all the limitations we know about MPC also apply in this case. So in particular, all of these protocols assume some flavor of an honest majority. So rather than just requiring that one party is honest, you need a majority of the participants to be honest. Otherwise, if there's a sufficient quorum of dishonest parties, they can get together and find out what the result is going to be earlier than they're supposed to in the protocol. So one thing that's been really exciting the last year, really year and a half, is that there's actually like a really nice implementation of this now that uses the threshold crypto approach. In fact, it uses like a really simple approach where you just do threshold BLS signatures, and each round of this beacon is just a signature on the round number and the result from the previous round. This DRAND beacon, which is now up and running. In fact, I'll do a live demo just for fun. Where is the actual beacon values? Yeah, so you can go to drand.love. It's actually a very good way to do it if you ever want to generate a random number for some kind of office pool or something like that. And you can see, this has been running for, well, this is like 700,000+ blocks now. And in a couple of seconds, we should get the next value, 256 new bits of entropy. So yeah, really neat. It's a running service. I think there are 16 organizations now that run nodes, including a couple of universities. Maybe something that blockchain at UBC would be interested in getting involved in. They say on their website that they will accept more participants. The more, the merrier. Yeah, that's like a really nice practical beacon that's up and running these days that you can use. Okay, but I guess the approach that I've worked on more, so I'm the most excited to tell you about is approaches using delay functions. Okay, so I think this is the last of these Alice, Bob, and Carol demos I have for you. But this will show you how remember the multi-party computation one, even the very simplified version, there was like lots and lots of stuff happening. With the delay function, it's the simplest protocol you can imagine. You just have every party publish their random nonce. So there's no commitment even, you just publish your nonce plain. And then the randomness beacon is some combination of everybody's nonce run through what's called a delay function. So you compose a delay function with some function that combines everybody's random input. That's the whole protocol. Okay, so why does this work? Well, you have some window in which people have to publish their random value. And that window is shorter than what you believe is the minimum amount of time that anybody can compute that delay function. So I'll talk more about delay functions, but to understand this protocol, you just need to know that they're functions that you can't compute in less than some minimum amount of time. So this is great. The last revealer attack that I said, kind of plagues all the other protocols is now gone, even though the protocol is much simpler. And the reason it's gone is that even if Carol is the last one to publish her random value, and even if she looks at the random values that Alice and Bob have published, she can try and take a guess about the effect of different random values she might publish. But she can't actually compute what the randomness beacon will be. And the reason is because of that delay function. So if Carol, tries to say, well, what if I choose this value, R sub question mark here, what would the randomness beacon be? That kicks off this, that requires computing this delay function, which is going to be this long process. And by the time she's computed it, by the time she figures out if this is a good value for her to choose, it's going to be too late. She's going to be out of this window in which she had to publish her value. So it's a really neat kind of very simple idea that if you just have a function that's slow to compute, you can sort of get rid of this whole family of attacks. The great thing about delay functions, we sort of get back to the stronger security model of like the simple commit reveal protocols of only needing one person to be honest, only needing one person to choose a truly random value. But we also don't need any big mechanism to punish people who abort the protocol. We don't need to have them forfeit, put up a bond or forfeit it. We just have to assume that this delay function is actually secure. And this actually works in a lot of other contexts too. So there's kind of this old idea of generating a beacon by hashing headers from the blockchain, um, which is pretty good, but there's some attacks on this as well. So this is like an idea that's been around since the early days of blockchains. And the attack, has also been known for quite a long time. And the attack is that, a miner can find a block and then they can say, well, what would happen if I actually publish this block? It would cause a beacon output I don't like. So they can choose, not to publish. They can wait for somebody else to find a block that hopefully gives them the beacon result that they want. Kind of a same idea with, reorganizations. So, say that two different blocks have been found, one of which, the green one produces a good lottery outcome and the red one produces a bad outcome. An attacker can try and get people to extend the chain, following up on what they consider the good blocks. So maybe they bribe people, maybe they just, rent a bunch of capacity, but they can try and force the chain onto the value that they want as a way of biasing the beacon. So same general approach applies. You take this source, the blockchain, which is sort of biasable. You add a delay function, a verifiable delay function. Hopefully, you get your beacon output that way. And it's really for the same reason that the simple protocol worked. If you make it so slow to compute what the implications are of some bias you might introduce, then an attacker won't know what to do before it's too late for them to act. So same idea kind of applies. If an attacker is trying to figure out, which of these two chains should I mine on, or should I bribe other people to mine on to get the output I want? If they're still stuck computing this slow delay function, they won't know which one to favor. And the same exact idea applies in the stock market case. So the attack in the stock market case is that you would look at what the closing prices of a bunch of stocks are about to be. To generate a beacon from the stock market, you presumably take a bunch of stock prices and run them through some hash function. So the idea is, an attacker can simulate lots of possible 1 cent, manipulations of a stock price to see what the beacon output would be, and they can choose the best one. But again, same exact idea. If you add a delay function, the attacker will be stuck computing. They'll be waiting for their computation to finish, and by the time it does, hopefully the market is closed and they can't act anymore. Okay, so hopefully I've convinced you of the promise of VDFs, as a crypto gadget that you can build. I'll just give you a little bit of background on what, a little more detail on what VDFs are and the current state of the art. So it's really a pretty simple function. There's just, we'd think of it as a forward direction and a reverse direction, evaluating the VDF and, just verifying that the evaluation was correct. And there's 3 security properties, and they're sort of all right in the name. Verifiable delay function. It should be a function that's, it's efficient to verify, so it's much more efficient to verify than it is to compute. It's a function that introduces a delay. That's the D part. So there shouldn't be any algorithm that actually evaluates this function that takes fewer than T steps, T sequential steps. So, basically we want the best known algorithm to evaluate this function to be inherently sequential with some parameter T that, you can specify at setup time. And then the F part is just that the output is unique. So it is a function, and that just means that everybody will get the same beacon output. Okay, so that's the crash course in VDFs. And I'll point out, sort of interesting. I guess actually, before we started writing papers about VDFs, it had been speculated in a few places that this was actually another trilemma, that you couldn't have VD and F all at the same time, because there were known constructions to get any 2 of the 3. But turns out it's definitely not a trilemma. We know how to get all 3 properties at the same time. In fact, if you use generic verifiable computation techniques, it's actually pretty easy. at least conceptually. It's, there's some tricks about doing this in practice and getting it efficient. But this was, probably the main contribution of our paper in 2018 on this, is to just say, you can take any one-way function, you can iterate it a certain number of times, which would actually be t, the number of steps that you want the computation to take. And then to get verifiability, you can sort of get it for free from generic verifiable computation techniques. So you could think you use a snark system, a succinct argument system, and you just produce a proof that this entire chain of one-way functions was computed correctly. Okay, so this is conceptually very, very simple. Actually getting this to be efficient in practice, like I said, is hard, but is doable. So that should sort of convince you that this idea of a VDF is even possible. But it turns out there's some algebraic ways to do this that end up being much more efficient. I think the simplest way to see this is to think of a simple thing like computing a square root, where computing a square root is much more expensive than verifying a square root. You can actually do this in a finite group, and then we know like exactly what the trade-off is. The ratio between evaluation time to compute a square root and verifying that the square root is correct is proportional to the size of the group. So this is kind of a starting point. This idea actually dates to like the early 90s. It was proposed as a proof of work. So before VDFs, before delay functions, cryptographers had noticed that square roots had this interesting property that they're much more expensive in one direction than the other direction. The modern version, which is a little bit different, you work in a group of unknown orders, so like an RSA group, a large composite whose factorization isn't known. And the function is actually just repeated squaring. So you just take your input and you square it t times, where t is the number of steps that the computation is supposed to take. So it's, we actually don't have a proof of it. It's just an assumption that this gives you a delay, that there isn't a way to speed this up. But it's fairly credibly believed. If RSA is secure, then this is going to be a secure delay function. So this we knew about for a while. It was proposed in the 90s actually for time lock encryption and other applications. But it wasn't until 2018 that we knew how you could actually verify this efficiently. And it was pretty amazing actually that we wrote our paper in 2018 about generic VDFs using succinct proof systems, and in only a couple months, two other papers came out that both provided ways to prove repeated squaring was done correctly in a group of unknown order. And these two constructions are like totally different. They have nothing to do with each other. They both came out, I think, in the same month, I think June 2018. And since then, we found no other constructions. So it was like two totally different constructions were found almost simultaneously, and then basically nothing since then except variations of these two. The details aren't super important. I'll maybe in the interest of time, I'll go through this quite quickly. But the slightly simpler of the two proofs, that's also a bit more efficient, so it's being used more in practice now. This is Wesolowski's proof. The idea conceptually is pretty simple. If somebody claims that they've taken this input x and they've squared it t times, you basically challenge them to provide a random point that is almost x to the 2 to the t, but not quite. And you do this in a bit of a funny way. You choose this prime L, and then they do long division. And that gives them this sort of random element that they have to compute, which is almost as big as x to the 2 to the t, but not quite as big. And then there's kind of a simple way for the challenger to check that, like, if they do a little bit more work, they get from this point to the claimed result. So there's a lot of details to actually make this secure. But that's kind of the general idea, which is fairly simple. If someone claims they've basically done all this work, this long exponent chain, you kind of query them on a random point that's like almost but not quite as much work as they did, and then you check that you really get to the endpoint that they claim. There's been lots and lots of other research since the initial VDF paper. All sorts of different sub flavors of VDFs have come around. There's this sort of industry consortium. We've had 4 workshops now just on VDFs. At least like 10 or 20 papers on ePrint that you can read with variations that have been proposed. Though, like I said, it's kind of still mostly the two different ways of doing a proof of squaring in a group of unknown order. There's a lot of practical challenges too, in addition to all the algorithmic work that's been done. In particular, like there's this question of how you can actually choose the parameters. So, the general assumption is you need this big number n that's a product of 2 primes, and for it to be a secure VDF, the requirement is that nobody knows P and Q, the 2 prime factors of n. Actually, it's called a trapdoor VDF if somebody knows those 2 factors, because they can actually compute it quickly. They don't have to do T steps. The choices right now are like have someone do a trusted setup, or do this expensive multi-party computation protocol. There is another approach, though. There's another type of group of unknown order that we know how to compute that can be constructed without a trusted setup. They're usually just called class groups, but the full name is class group of binary quadratic forms. So kind of interesting new area of crypto you can delve into if you're interested in how these things are constructed. There's a lot of open questions about how big these class groups need to be chosen so that nobody can compute the order. The sense is they're not quite ready for deployment yet, but they're potentially a way to use all these same protocols to build a VDF without the trusted setup. There's also a question of who's going to compute the VDF. Somebody has to do this slow computation. Most of the time, it's basically like a public good, so somebody is going to run this basically as a public service. I think one of the other really interesting things about VDFs is that they require thinking about how fast an attacker can compute this function. Traditionally in crypto, we think about scale. We think about how efficiently an attacker can try 2 to the 80 different possible values for a key. With VDFs, we don't have to think about scale. We have to think about acceleration and maxing out clock speed. Rather than having like a really big grid of computers, we're just worried about an adversary that invests a lot in one specific computing device. It might use exotic materials. It might use different semiconductors, whatever, that just goes as fast as possible. So it's been interesting, like having a few conversations with people who work on hardware and people in crypto who really haven't had to worry about adversaries like this before. But VDFs are coming in practice. So there was actually a practical rollout last summer by Starkware, which is a startup that does succinct proofs. So they essentially implemented the construction from our paper of the generic VDF from succinct proof. And there's also been a lot of work from Ethereum to have efficient hardware to compute an RSA-based VDF. The plan is that this will eventually be part of Ethereum 2.0. There will be a beacon built into it that people can use both for randomness and smart contracts and for the consensus protocol. The last question I guess I'll leave you with, which I promised I'd circle back to, although I guess I'm only circling back to it to say it's the unsolved part of this. The eventual dream that we'd really like to get to is to not just use randomness beacons and not just use VDFs for consensus protocols, but to actually run big high stakes lotteries in the real world, using these constructions, using cryptographically verifiable lotteries, using VDFs. But there's so many steps there. I mean, I've been talking at a fairly technical level for 50 minutes and I'm out of breath. And I skipped over a lot of details. So, I hope there'll be some questions coming back, but my point I'm trying to make now is that, if I had this much trouble explaining how all of this worked to, a technical blockchain audience, how are we going to make a TV show out of it? How are people going to be convinced that the FIFA World Cup draw was actually secure because some cryptographers told them that some crazy thing happened involving repeated squaring and beacons and a bunch of words that they've never heard of before. So I don't have a good answer for that, but I've always been interested not just in crypto and security, but usability and human factors and how people will perceive the technology. So hopefully this will be an interesting research area to jump into the next couple of years. How can we convince the public that some cryptographic protocol actually produced a fair outcome? So that's probably a good place for me to stop. And please ask any questions that you might have.
Wonderful. Thank you, Joseph. That was a really amazing talk. Super fascinated to get into this area with you. And I thought you explained it all, pretty well. Maybe not ready for the TV show just yet.
Yeah.
but definitely very understandable the way that you presented it. So I'm just looking at, for those who are participating, if you have questions, you could please put them in the Q&A section, or you might be able to post to chat. I think one of our participants was able to post to chat wherever, or open your mic and speak. There's 3 different ways for you to ask your question, so don't be shy. While you're maybe thinking about your questions, Joseph, I'm not a computer scientist nor a cryptographer. And so, of course, a lot of the details, the mathematical details, I'm not able to really engage at that deep level. So I'm seeing people's pictures coming up here. So I don't know if those who are opening up their mics maybe have any questions before I go on. But one thing that struck me is that, I'm aware that in the new Ethereum proof of stake consensus mechanism that they are moving toward, that a lottery, there's a lottery selection of verifiers, and I just wondered, your reflections. I don't know how closely you follow those discussions, or how in depth you've looked at what's being proposed, but I'm just wondering, based on what you've spoken about today and the different types of attacks and the pros and cons of different approaches, what your thoughts are on the current proposal for the proof of stake consensus mechanism for Ethereum.
Yeah, so I guess the full proposal for proof of stake in ETH 2.0 is pretty complicated, and I guess I don't want to comment on the general proof of stake part of it, but the randomness part that underlies it. They made a couple of specific choices. They chose to go for a VDF based approach rather than a MPC or kind of threshold crypto based approach, which I think is, I think it offers much stronger properties, and that, like I said, it only requires one participant to be honest, rather than a majority.
Mm-hmm.
But it requires relying on new crypto. It's kind of the more it requires less proven tools from crypto.
Mm-hmm.
Which still haven't really been available, because for VDFs to be useful in practice, you need like an efficient hardware implementation, and they've put a bunch of money into that. Hopefully it's here in a year or two, but there's just some delay for that.
Mm-hmm.
And they also chose, the specific VDF that they've chosen, they're gonna do an RSA based one. They aren't going for the also like sort of what would be a more aggressive approach would be to use class groups. I think that was the right choice to use RSA. I think it's like we have a much better understanding of how much that can be accelerated, and the difficulty of factoring. But it's introduced kind of the trusted setup problem. The plan has been to do a multi-party computation, which people have been working on, which also introduces like a bunch of extra complexity. So
Mm-hmm.
maybe it's like in line with general Ethereum thinking, that they went for like the generally more technically complicated way to do it that is better, hopefully offers better properties in the long run,
Mm-hmm.
rather than something easy to achieve today like the DRAND approach, that doesn't offer quite as strong of a security model.
Mm-hmm. Right. Yeah. Well, thanks for those reflections. I have, I could follow up. I have more questions, but I just want to make sure that I'm not overlooking questions from our participants. So if anybody does want to jump in with a question to ask Joseph, please open your mic or post to the chat now. No, no follow-up questions there. Everybody's feeling shy, weighed in on this topic. Well, as they say, fools rush in where angels fear to tread. So I will, I will ask another question. We're nearly at the top of our time anyway, but I didn't want to let you get away without asking you about some that came up on your Twitter feed. This is not to do with randomness and and VDFs. But there's been so much talk and so much buzz about NFTs lately. And I saw on your Twitter feed that you had created an commemorative NFT of your classic textbook. And then you tweeted that, as soon as you posted that, one of your students had found out a way to forge the NFT. So as this is, I'm interested in authenticity of documents, whether they're crypto documents or they're more traditional documents. I just wondered if you wanted to end on a comment on NFTs and your experience with NFTs at all.
Yeah, I mean, we mostly just did it for fun. Um, you know, it and it was kind of fun to see, that we got a couple of bids. I think it ended up selling for 1 ETH in the end.
Okay, not bad.
Yeah, depends on the day, I guess, how much that's worth. But yeah, no, it was interesting that someone tried to knock it off right away. I mean, I
Yeah.
think for any NFT, it's like I could sell you an NFT that represents Niagara Falls or The Godfather Part 2 or like anything in the world. I can claim to create an NFT for it, right? It Yeah, it only means something if there's some reason to believe that there's authenticity behind it.
Yeah.
In the case of the NFT for our book, we said all of the authors agreed to tweet it on their timeline to basically say like this is the genuine NFT representing our book. And the other NFT didn't have that. It just had the same metadata, but didn't have like a connection to our Twitter feeds. So it actually seems like it generally worked. Like I think nobody seriously bid on the other NFT. And similarly, like I think if you made an NFT and said this NFT represents Niagara Falls, like probably nobody would pay attention to it because they'd say, you don't have any authority to over that object in the real world. So yeah, I mean, sometimes I wonder with some NFTs, like why that NFT is the one that's valued over others. But generally, if it's like an artist or any kind of writer who's saying this NFT represents their work, then usually you have a clear authority who people are willing to give credibility to. So yeah, like it was perfect for teaching, I think, because we had the counterfeit and that and it didn't work because we took some simple steps to try to say this was the real one. So
Yeah, fantastic. Well, lots of fun, and thank you for your reflections on NFTs, and more substantively, thank you for your reflections on VDFs and problems of randomness. It's been really fascinating, and gosh, we do hope we can get you back and in person to engage more with our community. I think that there will certainly be more lively discussion if we were able to meet up in person, and I look forward to that day. So thank you very much for joining us. And of course, we recorded the session. So for those who haven't been able to attend in person, they'll be able to play it back and, maybe follow up with some questions at that time. So thanks again, Joseph, for joining us, for taking the time. And thanks for everyone who's joined the session today. And we look forward to seeing you again at future sessions. So bye for now.
thanks so much for having me. Bye,
Yeah,
everybody.
absolutely. Thank you. Bye. Bye, everyone.